section 3.4, we're going to discuss the topic of concavity and inflection points. Before we actually define these ideas, just want to remind us of the relationship between f prime, and f double prime. So remember, we use f as a general notation for the function, right? F prime, it turned out to be the rate of change of the function, right? That's what f prime is at any given point. So that's what that is. F prime is the rate of change of the function, which we call the derivative of the function. F double prime now, which would be the second derivative of the function, is the rate of change of f prime. Okay, that means itself is a rate of change of a rate of change. So in other words, we want to know how the rate of change is changing. Okay, so it's double change. And of course, the second rate of change is the slope. So we want to know how slope of the function is changing at what rate. Okay. Now, what we would like to do in this section, our objective is we would like to know at what point or points does the function change its rate of change. Okay, again, not the function itself directly, but rather indirectly. So let's define first of all what we mean by concavity of the graph of a function. So our definition of concavity of the graph of a function is going to be the following. Suppose we have a function that is differentiable on an open interval I. Then we say the graph of f is concave upward on that interval I if the derivative, the first derivative that is, the derivative of the function is increasing on I, and is said to be concave downward if the derivative f prime is decreasing on that interval I. So here I have some visuals for you of what those parts A and B mean. So in part A, again, we said concave upward if f prime, the derivative is increasing. So if you look at, for example, this first function I have here. So here's the function itself. And if you look at the slope of the tangent, I have it at a couple of points. Notice how slope is positive, but it's more steep or steeper, and that means the derivative is increasing, right? And look at the curvature of the function. It's curved upwards. So the concavity is what it is doing inside, if you will, of the curve, not what's happening on the outside, but rather inside. So it's pointing upward. Okay, in that case, the derivative is increasing. Now look at this one. It's still concave upward, and the derivative, although negative, but it's actually increasing. So it's becoming less of a negative, right? It's approaching zero. So if you look at the point here, the derivative is very negative, but it's negative still, but a lesser amount. And of course, it's approaching zero almost. So the derivative is, in this case, increasing again, but negative. And for both of these, the concavity is upward. Now, if you look at right next to that in here, for both of these curves are concave downward. Now, if you look at the slope of a tangent at this point is very positive, still positive up here, but it's a lesser of a positive, again, approaching possibly zero, or you could shoot up again. But for what I have, the slope is positive, but it's decreasing. And look at this other part of another curve. Slope's negative, and it's becoming actually more negative, which means in absolute sense the derivative is actually decreasing. Because think of it this way, it could have come from a case where it was horizontal, zero, then it became negative, and it's becoming more and more negative to where it almost approaches negative infinity the way I have it. So in all of these, both of these, the arrows point toward the concave downward. And here's a little bit more on that. So what do we mean again by concavity? The concavity of a curve shows the amount of bending or curl away from tangent line. So the case where here I have, again, on the left, I have a curve. Here's a tangent line at that point that I have at a low point. And notice how this function is bending away from the tangent line. So the concavity is upward. So it bends above the tangent line. Therefore, it's concave upward. And if you look at, actually for this one, my tangent line is not here. The tangent line should actually be over here. That's where the tangent line is. Okay. And for this tangent line, it's going to, again, bend downward from the tangent line. There. So this is where T, the tangent line, is. Okay. And that's what another way to think about the concavity is. And there you go. So because the curve lies below the tangent line, therefore F bends downward, and hence downward concavity or concave downward. Now, having talked about that, let's look at our first theorem. Our first theorem reads, the graph of a function f is concave upward on an open interval I where the second derivative is positive. In other words, the rate of change of the first derivative is positive. And remember, this is what we showed here, right up here, right? The derivative, the rate of change, and the derivative is positive. So that's what that says. It's increasing. So the second derivative is positive and is concave downward if the second derivative is less than 0. That's the definition of concave up and down. So second derivative positive, concave upward. Second derivative negative, it is concave downward. Now, we can define an inflection point or a point of inflection as a point where the concavity or the curvature of the function changes from up to down or from down to upward. Okay, either way. And that is an important point on the graph of a function, and in general for any model that uses inflection points. Inflection points are used quite often in all areas, but also they're quite often used in the field of economics. Usually a point of inflection shows the change in the market of some sort. It could be housing market, could be employment, could be inflation. So these inflection points are very meaningful in economics. Now, let's look at our other definition. This time we're going to look at the definition of point of inflections on a graph, the formal definitions. So suppose a graph of f has a tangent line, possibly vertical, at a point C and f at C, and the graph is concave upward on one side of P and concave downward on the other side of this point P. Then this point is called a point of inflection on the graph of a function. Okay, now just I have a note here about this, and then we'll see some graphs where I can clarify what the point of inflection looks like on the graph of a function. So at the point of inflection, either the derivative, the second derivative that is 0, or the second derivative does not exist. Now that's awful similar to what we said about the critical numbers of a function, right? Remember, f prime either at C exists and is equal to 0, or f prime does not exist. That was the very definition of critical numbers. So for the points of inflection, this is what we have exactly. The C here is going to be the critical number of the first derivative. And that's what f double prime at C is 0. and or does not exist. So now you're looking at a couple of sketches I have here. So this is a case where this is C. Notice the second derivative at C is 0 because the first derivative is 0 also, but also the second derivative is 0 here. And look at the curvature here. It's concave upward and concave downward. So this point is a point of inflection. Second derivative 0. Now here's a case where f double prime of C does not exist, namely because f prime does not exist. Remember, the tangent at C is vertical. So if the first derivative does not exist, the second derivative cannot exist either. And here again, you're looking at the portion of the curve where the concavity is downward and the portion of the curve where the concavity is upward. So both of these are points of inflection. Okay, now how do we determine these points of inflection? We're going to see it in an example. Now we're going to look at another theorem here. This is a second derivative test for extrema. Remember, in previous section we looked at the first derivative test for extrema. Now that we've talked about second derivative, it is possible to also use second derivative to determine the local extrema. Usually you use one or the other, but this is an option also. The first derivative test a lot of times is easier, but nevertheless, here it is. For second derivative test for extrema, that is. So we're going to assume that the function is continuous and has a continuous first as well as continuous second derivatives on the open interval containing a critical number of f. Okay, now this is critical number of f. Okay, be careful here. It is not critical number of f prime. Okay, the critical numbers of f prime are used for points of inflection. Okay, but the critical numbers of f, that's when you set f prime equal to 0 and you get those numbers. So for the test for extrema, the second derivative test for extrema, now you look at the second derivative at critical numbers of f, and if the second derivative at that point is negative, then we have a local max. If the second derivative is positive, then f has a local min at C, and if the second derivative at the critical numbers of f is 0, then this particular test, the second derivative test, is inconclusive. And the function may not have a local extrema. Okay. Now usually what happens is, there you go, if part C happens, then we pretty much are out of luck, right? We have to use first derivative test. Okay, but nonetheless this is an option using second derivatives. Now let's take a look at here. We're focusing on points of inflection again. Okay, so more specifically, I'm looking at a corner or a cusp. Okay. Now, a corner point or a cusp on the graph of a function may not be a point of inflection. It depends. So let's take a look at this made-up sketch that I have here. Okay. So I've got some points here, and this point, this point. These points are all points of inflection. Let's investigate the concavity. Concave upward, coming to the point, and then notice the curvature changes, right? If we draw a tangent line, it falls below the tangent line. It's below the tangent line, so the curvature is negative. If I draw a tangent here, above the tangent line, the curvature is positive. Okay, so there is a transition from up to down. Therefore, this is a point of inflection. Now, the curvature continues to be down, and then it transitions to concave upward. So this is also a point of inflection. Remember, point of inflection is a point where the concavity changes. And this is a corner point. The derivative is almost vertical tangent at that point, and it is negative looking at the other segment. So this is a corner point, but it is a point of inflection, right? Because curvature is up and then transitions to downward curvature. So that is a point of inflection. Now, check this out. This is a corner point, but if you look at the concavity, it doesn't change, right? At that point, it's down and it remains down. So this point, it is not a point of inflection. It is a cusp, but it is not a point of inflection. The concavity does not change. And then you go here. Once you hit that point where I have point of inflection, notice again, the curvature changes. Therefore, this too is a point of inflection. So hopefully this will put everything in perspective with respect to what is a point of inflection. Now, to find all of these points of inflection, we need to find the second derivative, and then determine if second, and then find, we need to find the second derivative and find the points where second derivative is either 0 or does not exist. Okay, and we will do that in the coming exercises. So let's begin with some of these exercises that I have copied from your textbook. So in this segment, we're going to take a look at exercise number, let's do numbers 4 and number 6 here. In exercise number 4, the question reads, now it says 1 through 6, so I just copied 4 and 6 in here. So 1, 2, and 3 are on the other page. So the exercise reads, you are given the graph of a function, and we want to determine the intervals where the graph of f is concave upward and where it is concave downward, and we want to find all inflection points of f. Okay, so in number 4, we go from left to right on these graphs to answer the questions. So coming from the left, look at the concavity. The curvature is up, and then it transitions to down, right? So this point must be a point of inflection, right? So for exercise number 4, I'm going to say that f is concave upward on, so far, the interval from negative infinity to 0. Remember, we're looking at the x value on the x-axis. We're looking at x values for which the function is concave upward. Now, and then the curvature is downward, but then notice in here it's upwards again, upward, upward, upward. Now, at some point here, the concavity has to change, right? So in fact, let me do this. I'm just going to do a blow up of this segment of the curve, right? So it looks like it's looking like that. And this is what I'm referring to, concave down, concave up. So maybe around here, wherever that point might be, this is going to be a point of inflection. Okay, and this number, the way they have this graph, probably the concavity changes at, there you go, at about when x is 1, right? Okay, so it's going to be concave. F is concave downward on from 0 to 1. Now at 1, because it's a transition point, we don't have brackets on these intervals. They're open intervals, not closed intervals. And then the curvature is always going to be up, right? It's always going to be up. And that means from 1 to infinity. Union 1 to infinity. That's how you work these. Okay, hopefully you can follow that. Let's take a look at number 6. In number 6 again, you go from left to right. So it's going to be concave down, concave up, remains up. So at some point, notice the up and down arrows come together, looks like at this point. So again, we have concave upward from negative infinity on the x-axis up to 0, and then it's going to downward, sorry. The arrows point down. Concave downward. And concave upward is going to be from 0 to infinity. All right, and that's what that is. Now, for like number 5, you can try number 5. Do the same thing I did. Concave down, down. Ooh, this is interesting. Down. So let's see if you can make the determination for number 5. All right. Let's take a look at this other segment of the exercises now. So in this segment now, we would like to, let me read the question now. Here the question reads, determine where the graph of the function is concave upward and where it is concave downward. Also, find all inflection points of the function. Now, we're not going to graph these, okay? We will do these graphs eventually in the next maybe 2 sections or even the next section. But for now, we just want to determine where the graphs will be concave up, down, and if there are any points of inflection where the concavity changes. Remember, the points of inflection are the points where the curvature changes from upward to downward or downward to upward. So let's take a look at, let's begin with exercise number 16. Okay, so in exercise number 16, here we are given g of x. Let me write this one. And g of x is 2x, negative x to 1/3, right? And so what do we need to do? Remember, for concavity, we need to go up to second derivative, right? And find the critical numbers of the first derivative. That is, I'll show you how to do that. So let's begin with g prime x. That's going to be 2 minus 1/3 x to 1/3 minus 1 is negative 2/3. Now don't simplify this. Okay, usually we simplify if you want to find the extrema using first derivative test, but that's not what we're doing in this section. So do not need to simplify that. G double prime, derivative of 2, 0. That's the constant multiple. Derivative of x to negative 2/3 is negative 2/3. X to negative 2/3 minus 1 is negative 5/3. Okay, now we do want to simplify this one. So let's go 2/9, and I'm going to put x to 5/3 in the denominator as a positive exponent. Okay, and there we have it. Now, just as before, we need to know the domain of this function. You have a polynomial function, a linear function, and you have cube root, right? X to 1/3 is cube root of x. So the domain is negative infinity to infinity. So the function is continuous, defined everywhere. Therefore, any critical number we get from the second derivative, it's going to be workable. All right, now let's do g double prime x equal to 0 and g double prime x undefined. And what we're doing, remember, this is exactly definition of critical numbers. But what we are finding is we are finding critical numbers of the first derivative. Okay, that's what we're doing. So let's see, we have a fraction. The numerator of the fraction is 2, so it cannot be 0. Therefore, g double prime x cannot equal 0 for this specific exercise. What about places where the second derivative is undefined? Well, in a fraction, we get into undefined situation where you have division by 0, right? Therefore, G double prime is undefined at, for this one, that's when x to 5/3 is equal to 0. And from this, we get x is equal to 0, right? So we only have one critical number of the first derivative. Now, let me do this. Hold on. What I'm going to do is I'm actually going to draw the number line. So this is our number line. This is now the second derivative. Okay, so please make sure that you follow the label on these number lines that I'm doing. Here's 0. Now, this is a 0 on the number line, right? Which happens to be the critical number at that point. So this is actually a critical number 0. And what we need to do next is we need to pick a test point. Okay, we're going to pick a test point. So for example, let it be 1. And we're going to plug in 1 into our second derivative. And remember, we're going to look at the sign. Although this is easy, 1 to any power is 1. So we get 2/9, right? Which is positive. All we care about is whether we have positive or negative. Therefore, that's going to be positive. Pick a test point, -1. Well, at -1, what are we going to get? We're going to get 2/9 times -1 to 5/3, which is cube root of -1 to the 5th power. And this is going to be less than 0. So the second derivative is going to be negative. The second derivative is negative to the left of 0. Second derivative negative, that means the graph is concave downward. Positive, it is concave upward. And indeed, there is a transition point from down to upward, isn't there? Right? So the point of inflection, is going to be at, now, we're talking about a quote-unquote point. A point has x and a y, right? So when we report the points of inflection, you put in 0, this is where it happens, and then you actually do the function, not double prime, the function. This is a point on the graph of the function. So you evaluate g at 0. Now g at 0 is 2 times 0 minus 0 to 1/3, and that's 0. So the point of inflection is going to be 0, 0. That's the answer to this exercise. Okay. And let's see. Now we're done with this exercise. That's all they ask for. So we did number 16. Let's take a look at another one. How about, let's take a look at, we can do numbers, let me do number 24 maybe here. Okay. Each of these have its own intricate detail. So let's take a look at number 24. In number 24, we have x squared minus 9 over 1 minus x squared. Okay. So this is exercise. Actually, let me move this other segment away so I can have more room to work with. Hold on. Okay, so question number 24, the function f of x is equal to x squared minus 9 divided by 1 minus x squared. So we need to find first as well as second derivative. Notice we didn't do anything with the first derivative. We're not doing that because we're doing something different. We're looking at the points of inflection. The points of inflection come from the second derivative. So for this one, let's use quotient rule. I have 1 minus x squared squared. Repeat the denominator. Derivative of the numerator minus numerator times derivative of the denominator. And then of course we need to simplify this, right? Okay, so it's 1 minus x squared squared in the denominator. So I'm going to keep 1 minus x squared squared in the denominator. Now in the numerator, let's distribute. We get 2x negative 2x cubed, distribute from the right. Same thing here, distribute from the right. Now the negative that's in front of 2x and this negative, they multiply to a positive, right? And then I'm going to distribute. That's going to be positive 2x cubed, and then negative of negative 9 of negative 2, that's going to be negative 18x. And I distribute it from the right. This will give us a couple of opposites. These are opposites, they add to 0. And this is going to be, I can factor, actually we have like terms, that's good. So f prime x, our first derivative, seems to be negative of 16x divided by 1 minus x squared squared. Okay, that's our first derivative. Now let's take the second derivative. Second derivative is derivative of the first, so f double prime x is going to equal 2. We're going to square the denominator. Now it's to the 4th power. Okay, then we're going to repeat the denominator, 1 minus x squared squared. Oh, and the negative, by the way, I'm going to keep it in front of the fraction line. Okay, and let me use, there you go. See that negative is now here. We can treat it as a constant multiple and keep it outside. But the constant here would be negative 1, multiple times the fraction. Okay, so you repeat the denominator, that's what I did here. You repeat the denominator, and then we multiply by derivative of the numerator minus numerator times derivative of this denominator, which is going to be, using the power rule, 2 times the binomial, and then chain rule times the derivative of inside, which is negative 2x. Okay, and let's see, this is equal to negative, and we're going to put 1 minus x squared to the 4th power. Now we need to simplify this work, right? So I'm going to distribute, expand the binomial and distribute. Let me see. Ooh, actually, here's a GCF, right? So I'm going to factor. That. We may have to distribute it, but we'll do it later. So let me factor it. 1 minus x squared factored. Okay, so that's going to make it 16 times 1 minus x squared. Remember, this first expression has 2 binomial factors, one of them removed, one remains. Oh, and also, 16. Let me factor 16 out also, because I see a 16 here and I see 16 here. Let's do that. Therefore, I'm going to have simply 1 minus x squared. I don't need parentheses on that. Now, negative, those multiply to a positive, so I'm going to go plus. The 16 is removed, and so is the binomial, right? Therefore, all that remains is 2x, and then this here I have 2x. Remember, the signs I already took care of. Negative by negative made positive. So that's going to be 2x and 2x. That makes it 4x squared, right? So I have 4x squared. That's when I multiply those two together. And then multiply that by, that's it, because 1 minus x squared was factored out outside. And there, that's all there is in this one. And we can now see that we can actually do this. We can cross out 1 minus x squared and 1 in the denominator, right? So again, let me do this. All of that is crossed out with one of these, leaving me with 3 binomial factor in the denominator. So I'm going to have negative of 1 minus x squared cubed, and in the numerator, 4x squared minus x squared makes positive 3x squared plus 1. Whew. And there you have it. So that's our second derivative. Now we need to find places where this derivative is 0 or undefined to find the points of inflection. Therefore, so this is f double prime x. We're going to set f double prime x equal to 0, and then we're going to also see where f double prime does not exist. Set it equal to 0. It's a fraction, so 3x squared plus 1 would be 0. 3x squared, and you can see that for real numbers, there's no way that will be 0 because you square the x. But I'm going to go through the motions. X squared equals negative 1 over 3. Now you can see x squared cannot be negative. The solutions to this are imaginary, right? Using I and all that stuff. So in other words, f double prime x, there's no way the numerator can be 0. So no critical number emerges from the numerator. Now let's see the denominator. If we set the denominator equal to 0 in a fraction, then division by 0 is undefined, which makes that derivative undefined. So here x squared is 1, x would be plus minus 1. So we get two critical numbers of the second derivative. And judging from our first function, this function, right? In this function, let's say the domain x cannot equal to 1 or negative 1, right? True? Because we have division by 0. So that's why it's important to keep track of domain of the function from the beginning. The function cannot handle 1 or negative 1. It doesn't exist. Look at these critical numbers are exactly what's not in the domain. So these, I'm going to write it, they're not in domain of the function. Okay, and therefore these cannot be point of inflection. Therefore there are no points of inflection, because the only place it could happen is where the function isn't even defined. Let's do our sign chart. So I'm going to go, here's negative 1 and here's 1. And then we're going to pick test points like 0 here, pick 2 here, pick negative 2 here. Now we're looking at second derivative, okay? The sign on the second derivative. And our second derivative again is right up here. This is our second derivative, right? So I'm going to plug in a 0 into our second derivative. Let me go f double prime at 0. It's going to be negative of, at 0 the numerator is positive, the denominator is positive. So we have negative of a positive, it's going to be negative, right? So that means you have a second derivative that's negative. And then I'm going to pick f double prime at 2, my test point. That's negative of the denominator when x is 2. When x is 2, you get 1 minus 2 squared. That's negative 3 cubed. The denominator is negative. The numerator is going to be, well, 2 squared is 4 times 3 plus 1 is positive. So you have negative of a negative fraction, that makes it positive. Therefore, at that test point, the sign on the second derivative is positive, and f double prime at negative 2 is negative of, now put in negative 2 here. 1 minus negative 2 squared, that's 1 minus 4. We cube it, so it's going to be negative. The denominator will be negative. The numerator is going to be positive. So we have negative of a negative fraction, that makes it positive. All right. And we got this one. So what is this telling me now? Well, all the plus signs means concave upward, and all the negative signs on the second derivative means it's concave downward. So the function is concave upward there, downward here, upward here. Now ordinarily this would be a point of inflection, wouldn't it? Oops, sorry, I don't know what happened. That's okay. There you go. Ordinarily, that would be a point of inflection, right? But because the function does not exist at 1 or -1, therefore this cannot be a point of inflection, right? That's what I had, I believe. Okay. But we can determine if the question asks, like, find the interval over which is concave up and down, we can answer those. But this question asks, find the points of inflection. So, number 24. Number 24, the answer is there are no points of inflection. Okay. Let's take a look at, let me see, we did number 24. Let's do another one. How about a trig one? Number 28. Between 0 and 4 pi, x minus sine x. Okay. X minus sine x. This one. Okay, well, let's do this one. X minus sine x. So, like before, I need to find first as well as second derivative. F prime x is going to be 1 minus cos x. F double prime x, derivative of 1 is 0, derivative of cosine is negative sine x. So the second derivative is just sine x. That's going to be easy. Sine x is a trig function and it's continuous everywhere. So there's no way the derivative isn't defined, the second derivative that is. So we're just going to set f double prime x equal to 0. That means sine x equals 0. And the zeros of sine are, again, k pi, where k is an integer, right? Okay. Now we are given 0 to 4 pi, right? So in that interval, the zeros are, and remember, for critical numbers, we look at the open interval, right? So the zeros are in the open interval from 0 to 4 pi. Let me just write this. This is from 0 to 4 pi open interval. X is going to be pi, 2 pi, and 3 pi, right? Those are the critical numbers. And then we can actually draw the number line. This is the second derivative. Here is 0, pi, 2 pi, 3 pi, 4 pi, like that. Pi, 2 pi, 3 pi, 4 pi. Now for derivatives, we look at the open interval. That's why we didn't include the endpoint. The function, you may say, but it's given 0 to 4 pi. The function actually is defined from 0 to 4 pi, but for the derivative, we only look at the open interval. Okay? Because we're looking at interval over which, not at the point at which the concavity is up or down. Okay. And then we are back to picking test points. I'm going to pick a test point here. Remember, our second derivative is just a sine function. So I'm going to go pi over 4 here. Test point here. Between pi and 2 pi, let's go, 3 pi over 2. That would work. And let's see. Between 2 pi and 3 pi, let's go, that's going to be 1, 2, 3, 4, 5 pi over 4. Yeah, that would work. Right? I'm thinking this. We're at 2 pi plus another pi over 4. 2 pi plus pi over 4. So that's going to be 9 pi over 4. There, let me change that to 9 pi over 4. And between 3 pi and 4 pi, well, 3 pi add another pi over 4. Just go 45 degrees more, that would be 13 pi over 4. These are my test points. Okay. and you can verify that these fall into those intervals. And all we have is sine. So let's do sine of pi over 4. Sine of 45 degrees. Remember, we just want to know if it's positive or negative. In the first quadrant, sine is positive, so it's going to be plus, plus, plus. At 3 pi over 2, sine of 3 pi over 2, that's going to be sine of 270 degrees, negative 1. It's going to be negative. Sine of 9 pi over 4, again, that's the reference angle is pi over 4. So that's going to be sine of pi over 4 positive. And looks like this should be negative. But again, you can verify those. Now, as far as the curvature goes, concave upward, right? Concave down, concave up, and concave down. And these critical numbers that we found they're all inside, right? All of these are inside the interval where the function is defined. So where the concavity changes, we have a point of inflection. So we do have a point of inflection, points of inflection. And again, I emphasize these are points. They will have an x and a y, not just an x. So the point of inflection is going to be pi and f, not f double prime, f at pi. It's a point on the graph of a function. The other one is going to be at 3 pi over 2 and f at 3 pi over 2. And the last one is going to be, oh, actually that was the second, not the last one, next to the last one. Oops, what am I doing? Inflection points, that's going to be 2 pi and 3 pi. Okay, so it's going to be at pi, f at pi. Okay. Next one is going to be at, I did pi, so this is 2 pi, right? I've reached the second critical number. Then it's 3 pi. It's going to be at 3 pi and f at 3 pi. And there we go. That should do it now. So, on the function, the second derivative was sine. Pi and sine of pi, right? Oh, we're going to f, not the derivative. We're going to f. Let me write it. F at pi is going to be pi minus sine pi. Remember, x minus sine x. Sine of pi is 0, so it's just pi. F at 2 pi is going to be 2 pi negative sine 2 pi. Again, all multiples of pi for sine would be 0, so that's just 2 pi. The next point of inflection is as 2 pi and 2 pi. And f at 3 pi is x, which is 3 pi, minus sine of 3 pi. And that's 3 pi. So it's 3 pi and 3 pi. And here we go. So those are all points of inflection, and we can actually we could graph this in Desmos and see what it looks like. Maybe I'll do that. Let me go graph it and I'll copy paste it in here for you. Okay, so there you go. I went ahead and graphed this in Desmos, and I'm going to show you now what this is showing us. So between 0 and pi, concave up. So every pi, the concavity changes pretty much, right? From up to down to up to down. Okay, and here's the graph. Now you're looking at the graph here. So if I just show you this one, so here you go. Curvature is upward. At pi here, the concavity changes to downward. That's what those numbers, the plus minuses, are telling us. And then at 2 pi, so it goes from down to up again. The transition points are points of inflection. And then 3 pi to 4 pi, it transitions to downward. And there you have it. And these points, here is a pi, point of inflection. Here's another one, point of inflection. Another one, a point of inflection. And there you have it. Okay, so let's take a look at another example here. Let's see. Let's do, how about, let's take a look at number maybe 32 would be good to look at. Let's check out number 32 in this segment. So this is number 32 now. We have sine x over 1 plus sine x between negative pi over 2 and 3 pi over 2. Okay, and these are open intervals, by the way. Check it out. They're not closed intervals. So I'm going to do that. Let me move this. Let me move this down so I have room to do this exercise. Okay. So we're doing exercise number 32 now. In exercise number 32, we have f of x is equal to, let me make sure I copy this exercise right. This was x minus sine x, right? It looks like I did x plus sine x. Hold on just a moment. Let me make sure I graphed the right function. No, we're good. We're good. We're good. Never mind. Okay, in number 32, we have f of x is equal to sine x over 1 plus sine x. And the interval is from negative pi over 2 to 3 pi over 2, open interval this time. Okay, so let's find our first derivative. F prime x is going to be square the denominator, repeat the denominator. Derivative of sine is cosine, minus numerator times derivative of sine, which is cosine x. That's the derivative of the denominator. So our first derivative, therefore, is going to be, let's see, our first derivative will be, here's the denominator, 1 plus sine x squared, true? And in the numerator, we can distribute cosine x to the binomial, so it becomes cos x plus sine x cosine x negative sine x cosine x. And indeed, those are opposites, they add to 0. So our first derivative is just cosine x divided by 1 plus sine x quantity squared. That's our first derivative. Now the second derivative, f double prime x is equal to, let's square the denominator, 1 plus sine x quantity to the 4th power now. Repeat the denominator times derivative of cosine, which is negative sine, minus the numerator. Derivative of the denominator is going to be, using the power rule, it's going to be 2 times 1 plus sine x, and then derivative of inside is cos x. Okay, so that's what we have. Now, let's see. We can factor 1 plus sine x, right? Because it's common to both of them. And we can also factor, in fact, a negative sign. So it's going to be negative 1 plus sine x factored out. Leaves me with 1 plus sine x, another binomial factor, times sine x. We factor the negative, so now I have 2 cosine squared x, right? Cosine x gives me cosine squared x. All of that divided by 1 plus sine x to the 4th power. And we can cross out actually the binomial in the numerator with one of the binomials in the denominator, that leaves me with sine x times 1 is sine x. Sine x is sine squared x, and the cosine x, oh, this is actually plus, right? Plus cosine. Oh, I'm sorry. Cosine squared. Remember, the negative is factored out, it's in the front, right? So it's not negative cosine. Glad I caught that early. Plus 2 cosine squared x. All right. Now, let's see, what else can we do with this one? Over the denominator, of course, 1 plus sine x cubed. Okay. And let's see. I can write everything in terms of sine, couldn't I? Let's do that. Let's write everything in terms of sine. So that means cosine squared x. This is going to be negative of sine squared x plus sine x. I swapped out the first two terms. These two swapped out. So I have it in descending powers of x plus 2. Now remember, cosine squared x is 1 minus sine squared x. So it's going to be 2 times 1 is 2, and then 2 times sine squared, negative 2 sine squared x. So use this identity in place of cosine squared x and multiply it by 2. Divided by 1 plus sine x cubed. And now I can combine like terms in the numerator. Get negative sine squared x, right? Got 2 of them here, 1 here, so those combine. And plus sine x minus plus 2 divided by 1 plus sine x cubed. Of course, we can distribute the negative throughout, and that will give me the derivative in terms of just a fraction, a positive fraction. So this will be sine squared x negative sine x minus 2 over 1 plus sine x cubed. Now in the numerator, actually, we have a function or an expression that is quadratic in form. Quadratic in form, that means I can factor the numerator. This is, the numerator is going to be sine x minus 2, and I'm running out of room here. F double prime x is equal to, hold on. Okay, f double prime x is going to equal to, this is sine x minus 2 times sine x plus 1 divided by 1 plus sine x, which is the same as the binomial in the numerator cubed. So that's good. You can cross yet another binomial factor, and so this is going to make it sine x minus 2 divided by 1 plus sine x squared. Okay, this is our second derivative. Now, let's check out the critical numbers of this one. The critical numbers, again, are places where denominator is 0 or or the derivative does not exist, right? So f double prime of x equals 0. So sine x minus 2 equals 0. That means sine x equals 2. This is impossible. Remember, sine fluctuates between 1 and negative 1. So there's no way sine can be 2. So there's no critical number coming from this. The denominator f prime doesn't exist when 1 plus sine x is 0. So that means sine x equals negative 1, and x must be 3 pi over 2. right? 3 pi over 2. And then, of course, there are 2k pi multiples of that. Every 360 degrees you reach that point. Now let me go back to my interval that I'm given. Our interval is between negative pi over 2 and 3 pi over 2, right? In other words, if I look at the circle here, negative pi over 2 in a clockwise direction, negative pi over 2, 3 pi over 2, so you go this way, there, to here, right? So you have one complete rotation of a circle, but the rotation begins at negative pi over 2, and this is 3 pi over 2. Puts you back exactly where you started at. But remember, both of these points are open circle, right? It's open circle at that. And there we have it again. That's the rotation. So there is no critical number. There are no critical numbers in this one. Okay, there are no critical numbers, because the way the interval is given in this exercise. So what is this telling us now? Let's draw the number line. F double prime, and this is a number line. So, but if we had critical numbers, they would be at 3 pi over 2, and then every 360 degrees. So let me just do this. If I pick a number here between 0 and 3 pi over 2, for example, I'm picking a test point here, 3 pi over 2, so I'm going to go pi. Okay, and then let's check out the second derivative at that point. F double prime at pi is equal to sine of pi minus 2 over 1 plus sine of pi squared. The denominator is always positive, agree? Because you're squaring the denominator. So denominator is always positive. Oh, interesting. Sine of pi is 0, the numerator is negative, right? So this is going to be negative. Now, I just noted something. If you look at this expression, go back up here. Sine x minus 2 is less than 0, always negative, right? Because the maximum sine x can be is 1, right? 1 minus 2 is negative 1. Got it. So we can actually do this. We don't have to pick more test points. If you did, this is what you're going to find out. This thing is always negative, the second derivative. F double prime x is less than 0 always. Always negative. And the reason for that is because numerator is always less than 0, because sine x minus 2 is less than 0, right? You can try all values for sine x between negative 1 and 1, because sine is range bound between negative 1 and 1, and minus 2, that's always negative. Denominator is always positive because of a squaring effect. So this fraction is always going to be negative divided by positive, which is negative always. All right. So the second derivative is always negative. Always negative, that means this function is always concave downward. Okay. It's always concave downward. So the answer is the function concave downward, right, on the interval that they gave us from negative pi over 2 to 3 pi over 2. Okay, and that's what that is. And I'm going to graph this function for you so you kind of see what is going on with this function, with number 32. It's an interesting function. Okay, but we're done with this exercise. I'm just going to go to Desmos, graph this, and then plot it. Come back and paste it into my note. So I'll come back in a moment. Okay, I'm back. So there you go. This is what this function looks like. So as you can see, it's always interesting. It's always concave downward over the entire domain. And of course, there are discontinuities, right? Places where denominator is 0, which we already know where they are. They are every 3 pi over 2, and at 3 pi over 2, that's the first one is right in here, 3 pi over 2. Okay, and then every 360 degrees thereafter. But the one interval in particular that was of interest to us, that was from negative pi over 2 to 3 pi over 2. So roughly this is what it looks like. And there you go. This here is at negative pi over 2, and this here is 3 pi over 2 is roughly here. There you go. This is at 3 pi over 2. And you can see, of course, it's always concave downward. Okay, and there's no point of inflection there. The concavity never changes. Okay, so we are done with this exercise. Let's take a look at now something in another segment of the exercises, something that's different now. In this segment of the exercises now, we are given a description of a function, right? We don't actually have a function itself. We simply have a description of a function, and we want to sketch the graph of a function having the given properties. All right, so let's take a look at an even number. How about let's take a look at number 50, for instance. Okay. All right, so in number 50, we are given that f at 0 is negative 1. So we need to transfer all this information on the graph of a function. So here is my xy coordinate system. Okay. Now we are given 3 points on the graph of this function. F at 0 is negative 1. So here's 1 point. F at negative 1 equals F at 1 equals 0. So those are actually the x-intercepts, right, of the graph. This is at, let's say, 1. This is at negative 1. Okay. And then we are told that f prime at 0 does not exist. So the fact that f prime at 0 doesn't exist means we either have a corner or a cusp. We could have a vertical asymptote. However, we are not told f at 0 does not exist, so we cannot assume there's a vertical asymptote. So we're going to, in other words, assume f exists at 0. The function does exist, and if the derivative doesn't exist, means there's a corner or cusp. Okay, so we'll keep that in mind. Now the derivative, the second piece of information here, or the other piece of information, the derivative is negative from negative infinity to 0. So that means the function must be decreasing. And we're going to put that together with the knowledge of f double prime x. Okay, f double prime is negative on negative infinity to 0. See, I'm looking at comparable interval. So putting these two pieces of information together, the function is decreasing and the second derivative is negative. That means it's concave down. Decreasing, concave down. And it's got to go through these 2 points. So the only thing I can think of is something like this. Okay, so it's coming together there. So if you look again, the function is indeed decreasing and concave down. And then we're going to look at the other segment, the other piece of information. The derivative from 0 to infinity means to the right of 0 on the x-axis. This function is increasing, but still 0 to infinity, concave downward. Increasing, but concave down. And it's got to go through 1. So there you go. This is the best I can do with this function. So this indeed, and at this point, it doesn't look like a cusp. It's more of a corner point. Because usually with cusps, it goes deeper. You see that? The difference between there and what I have. So this would be the graph of this function. Okay? And that's how you graph these. We don't know the function, but given those specifics, we can actually graph it for number 50. Now, let's take a look at number 52 in this case. Okay? In number 52, again, we are given, so let me go up higher, and we're going to graph number 52 here. For number 52, there, here is x. So we are given f at -1 equals f at 1 equals to 2. So we are given 2 points on the graph of the function again. F at -1, f at 1 or 2. So here's a point here and a mirror image here. Okay, right in here. Now, f prime at -1 equals f prime at 1 equals 0. Now, if the first derivative is 0, that means we have a horizontal tangent. At -1 and 1, there is a horizontal tangent. Okay, so again, from this we know that we have HT, horizontal tangent at these. That's what I gather so far. We have horizontal tangents. Now, the first derivative is negative, from -infinity to -1. So the function is decreasing actually from -infinity to -1, right? So the function is decreasing. It could be like that. And from 0 to 1 also it is decreasing. So it could be like that, also decreasing. You see both of these, the function is decreasing. Okay. And let's take a look at this next line. Here, the derivative is now positive, so the function is increasing. From -1 to 0, the function is increasing. So it could be, it's increasing, and also increasing from 1 to infinity. There you go. And remember, at 0, let's see, right here, the limit of f of x as x approaches 0 is infinity. That means as you go to 0 from the left, as you go to 0 from the right, the function gets very large. There you go. Okay. And notice infinity is not a number, so that means the function does not exist. From this information, I know f does not exist at x equals 0 because the function is approaching infinity. All right, what about the concavity? It's concave upward, right? F double prime positive means it's concave upward. From -infinity to 0, 0 to infinity means everywhere except at 0. Concave upward, upward, upward. So actually, looks like we're looking at the graph of this function. So let me now finalize it. I'm going to put it all together and show you what this graph looks like. So this was the vertical axis, right? The y-axis. And the graph of this function is going to look like this. And if you look at it, looks like it's an even function, so I'm going to make it symmetric. Okay, there, and this will be the graph of this function. Okay, and sorry about this, let me finish this portion of it. There. Okay, and with that we are done with this exercise. That's good enough. This height, this occurs at 2, right? We have the horizontal tangents. This isn't part of the graph, right? Only the red curve is the graph. And remember, it doesn't cross the vertical axis because we have a vertical asymptote at 0. The limit approaches infinity, and that makes it better. All right, and with that we are done with the exercises in this section, and in fact we are done with section 3.4. Hopefully you followed everything we've done, covered a lot of ground in this section, and we are done with this lecture.